Introduction to Battery Technology, Chapter 1, Introduction. Welcome to the Introduction to Battery Technology course, Chapter 1, Introduction. In this chapter, we'll set the stage for understanding the fundamentals of battery technology. This introduction will give you a big-picture view of what batteries are, why they matter, and how we'll approach learning about them throughout the course. Learning objectives. First, we'll gain a broad overview of the basics of battery technology. This will give you the foundation you need before diving into advanced topics, such as lithium-ion batteries. Think of it like learning the alphabet before writing essays. The fundamentals we cover here will make complex topics much easier to grasp later. To start, we look back at history. The voltaic pile, created by Alessandro Volta in 1799, was the first electrochemical energy storage device. Imagine the significance. For the first time in human history, we could store and use electrical energy in a controlled way. That moment set the stage for everything from flashlights to electric vehicles today. Terminology. Before we go deeper, we need to be comfortable with key terminologies. Electrode. This is the part of a battery that connects the external circuit to the internal chemistry, allowing energy to flow. Electrolyte. Think of this as the medium that allows ions to move between the electrodes, enabling the battery's chemical reactions. Active electrode. This is the electrode that participates in the electrochemical reaction. Its mass changes as the battery charges and discharges. Anode. The negative electrode where oxidation happens. Electrons are lost here. Cathode. The positive electrode where reduction happens. Electrons are gained here. Cell potential. This is the electrical pressure that drives electrons through the circuit. Galvanic cell. A system that produces electricity from spontaneous chemical reactions, also called a voltaic cell. These terms will frequently appear throughout our course, so it's beneficial to take the time to remember them. Galvanic cell and electrolyzer cell. Here's a simple but important distinction. In a galvanic cell, or voltaic cell, chemical energy is converted into electrical energy. In an electrolyzer cell, the opposite happens. Electrical energy is used to drive chemical changes. This is one of the first significant concepts to grasp when studying batteries, and it will help you make sense of how different battery systems operate. Examine the diagram closely to understand the concepts being presented visually. Galvanic cells. Now let's talk about types of galvanic cells and related systems. Fuel cells. These devices generate electricity as long as you supply reactants, such as hydrogen or oxygen, from external sources. They are typically not rechargeable. Batteries. These devices contain a limited supply of reactants. Once they are depleted, the reaction ceases, unless it is a rechargeable battery. There are two types of batteries, primary and secondary. Primary batteries. Your reliable, single-use power solution. No recharging needed. Perfect for all your everyday devices. Discover the benefits of secondary batteries. These rechargeable options, including lithium-ion and lead-acid, offer exceptional performance and sustainability. By choosing these innovative power sources, you not only enjoy convenience, but also contribute to a greener future. Make the smart choice today. Flow batteries. These combine characteristics of secondary batteries and fuel cells by storing reactants in external tanks. Metal air batteries. Use a metal anode and oxygen from the air as the cathode reactant. Knowing these categories will help you place different battery technologies in context as we move forward. Galvanic cells, lithium-ion batteries. Now let's look at a lithium-ion battery as an example of a galvanic cell in action. In this case, lithium ions move from the anode to the cathode through the electrolyte during discharge, releasing stored chemical energy as electrical power. When we recharge, the process is reversed. Electrical energy is used to push the lithium ions back to the anode, ready for the next cycle. These batteries are popular because of their high energy density, long cycle life, and relatively low self-discharge compared to other rechargeable batteries. Remember the key advantages of Li-ion batteries, which include their high energy density, extended cycle life, and minimal self-discharge. These features make them an ideal choice for a wide range of applications. Galvanic cells, alkali fuel cell. Here's another example of a galvanic cell. The fuel cell, specifically an alkaline fuel cell. Instead of storing the chemical reactants inside the cell, a fuel cell continuously receives fuel, such as hydrogen, from an external source. In the process, chemical energy from the fuel is directly converted to electricity. This technology is used in some vehicles, spacecraft, and backup power systems. Unlike batteries, fuel cells don't run down, which means that they don't lose power as long as fuel is supplied. As shown in the diagram, alkali fuel cells consist of 4 components: an anode, a cathode, separators, and an electrolyte, along with a supply of fuel sources and an outlet for byproducts such as water. Primary battery. Primary batteries are the type that can't be recharged. Once the stored chemical energy is used up, the battery is discarded. Common examples include alkaline batteries used in flashlights, remote controls, and toys. They're typically inexpensive and have a long shelf life, making them great for occasional use, but not for situations that require regular recharging. Secondary battery. Secondary batteries, also called rechargeable batteries, on the other hand, can be recharged multiple times. Examples include lithium-ion, nickel metal hydride, and IMH, nickel-cadmium, NCD, and lead-acid batteries. These types of batteries play a critical role in a wide range of applications due to their ability to be recharged and reused. Each battery type is engineered to suit specific needs, from high current bursts in automobiles, lead-acid batteries, to long-term, maintenance-free operation in powerboats and cameras, gel and sealed lead-acid batteries. The unique characteristics of these batteries, such as their charge/discharge cycles, electrolyte management, and gassing prevention, make them ideal for diverse applications, including electronics, security, and renewable energy storage. They may cost more upfront, but over time, they're more economical and sustainable since they can be used repeatedly. This is the type of battery you'll find in your phone, laptop, or electric vehicle. The diagram shows 4 different Li-ion batteries, classified by their external shape or packaging type. They are button or coin cells, cylindrical cells, prismatic cells, and pouch cells. Primary cell versus secondary cell. Let's compare primary and secondary cells. Primary cells are single-use, offer convenience, and have a long shelf life, but generate waste once depleted. Secondary cells require an investment in chargers and maintenance. However, they save money and resources over the long term. The choice between the two often depends on the application, how frequently the device is used, and whether recharging is practical. When comparing primary cells and secondary cells, the most important distinction lies in their chemical behavior. A primary cell is designed for single use only, because its electrochemical reactions are irreversible. Once the active materials inside are consumed, the cell cannot be recharged. Structurally, this is reflected in its simple design. The zinc can serve as the anode, the carbon rod acts as the cathode, and an electrolyte paste fills the gap between them. This simplicity makes primary cells compact, inexpensive, and ideal for low-drain applications, but they also come with higher internal resistance and a limited lifespan. In contrast, secondary cells are built around reversible chemical reactions, which allow them to be recharged many times. The design is more complex, with a dedicated anode, cathode, and a separator immersed in liquid or gel electrolyte to enable the back-and-forth movement of ions. This gives secondary cells lower internal resistance, higher current capacity, and the ability to deliver far more energy over their lifetime despite a slightly lower energy density per cycle. They require a higher initial investment, but the cost is offset by their long service life and suitability for demanding applications such as electric vehicles and portable electronics. That is why lithium-ion batteries, as a type of secondary cell, have become the backbone of modern energy storage. offering the rechargeability, efficiency, and design flexibility required for today's advanced technologies. Other types of batteries. Some batteries are designed for very specialized uses. For example, reserve batteries can be stored for years without losing their charge because the active materials are kept separate until needed. When activated, maybe by inserting an electrode or adding a liquid, they suddenly become operational. This makes them ideal for emergency or military equipment where reliability after long storage is critical. Then there are thermal batteries, which rely on heat to activate the electrolyte. They don't sit there gradually losing energy. Instead, they only come alive when exposed to heat. These are used in defense and aerospace because they can be stable for long periods but instantly deliver power when triggered. Finally, flow batteries store energy in liquid electrolytes kept in tanks outside the main cell. When you need power, those liquids are pumped into the reaction chamber. It's almost like fueling an engine, but instead of burning fuel, the liquids exchange ions to generate electricity. This design reduces wear and tear and makes the battery easier to scale up for large systems. Let's talk about the flow battery further. Flow batteries operate in a unique way. Think of them as a hybrid between a battery and a fuel cell. Like batteries, they can be recharged. But like fuel cells, their active reactants are stored outside the cell and pumped in as needed. This separation of reactants and reaction site helps prevent unwanted chemical reactions, extends life, and makes it easier to upgrade or repair parts. The diagram shows how the electrolyte flows from reservoirs through the cell and back. Battery components. Every battery, no matter the type, is built around three essential components: the anode, the cathode, and the electrolyte. Think of the anode as the starting point, where electrons are released, and the cathode as the destination, where those electrons are accepted. The electrolyte lies in between, acting like a special highway. It allows ions to travel back and forth, but it blocks electrons, forcing them to move through the external circuit instead. This separation is what powers our devices. To ensure safety, there's also a separator, a thin but strong barrier, like a fence that keeps the two electrodes apart while still letting the ions slip through. Without it, the electrodes would touch, causing a short circuit and immediate failure. Now, what really makes a battery fascinating is how these roles shift between discharge and charge. During discharge, when the battery is powering a device, the anode gives up electrons, sending them through the external circuit to the cathode, while ions move through the electrolyte to keep balance. The flow of electrons outside the battery is what runs your phone, your laptop, or even an electric car. But during charging, the process reverses. An external power source pushes electrons back toward the anode, while ions migrate the other way through the electrolyte. In this moment, the anode becomes the receiver, storing up energy for the next cycle, while the cathode temporarily gives up what it had gained. In simple terms, the anode and cathode are like two partners exchanging energy, while the electrolyte and separator carefully manage the traffic between them. This dance of electrons and ions, forward during discharge and backward during charging, is the heart of every rechargeable battery. Energy conversion in batteries. At the heart of a battery, all are the electrochemical reactions. Electrons are transferred between the anode and cathode via an external circuit, while ions move through the electrolyte. Here's how it works. At the anode, oxidation happens, the material gives up electrons. Those electrons travel through the external circuit, powering your device. Meanwhile, ions move through the electrolyte to balance the charge. At the cathode, reduction happens, electrons are taken in. This continuous movement of electrons and ions is what transforms chemical energy into electrical energy. It's a beautiful dance between chemistry and physics that allows a tiny metal and liquid package to power your phone, your car, or even an entire building. Charge and discharge process. Let's talk about what happens when a battery discharges and charges. Discharging, when the battery delivers energy. On this slide, we see the moment when the battery powers our device. Electrons leave the anode and travel through the external circuit, doing useful work as they pass through the device. At the same time, inside the battery, lithium ions move through the electrolyte toward the cathode, keeping the system balanced. In other words, electrons flow outward through your device, while ions flow inward through the battery, completing the cycle of energy delivery. Charging, when the battery stores energy again. Now, let's look at the reverse. When a charger is connected, external electrical energy forces electrons back into the battery. Electrons are pushed from the cathode toward the anode, where they are stored. Meanwhile, inside the battery, lithium ions also reverse direction, shuttling through the electrolyte back toward the anode. So, charging is essentially the journey of both electrons and ions returning home, storing energy for the next use. In lithium-ion batteries, lithium ions shuttle back and forth through the electrolyte between electrodes with each cycle. It's like a pendulum swinging. Discharge pushes ions one way, charging pushes them back. Electrode selection. When we make a battery, the choice of electrode materials is one of the most critical decisions because the voltage of the cell depends directly on the potential difference between the anode and cathode. In simple terms, the bigger the difference, the higher the cell voltage. For the anode, we look for metals that are light and willing to give up electrons easily. Lithium is the star example. If you look at the periodic table, lithium sits in group 1, the alkaline metals at the very top left corner. These elements are highly reactive because they have just one electron in their outer shell, and lithium, being the lightest solid metal, provides an excellent balance of low weight and strong reducing power. For the cathode, we often use compounds that contain transition metals combined with highly electronegative elements. In Li-ion batteries, cobalt, nickel, or manganese oxides are common. On the periodic table, these transition metals sit in the central block, while oxygen is on the far right, close to fluorine, one of the most electronegative elements. Cathode materials act like strong electron acceptors. Now, if we look at actual numbers, the standard electrode potential of lithium metal is about minus 3.04 volts versus the standard hydrogen electrode. A typical cathode, like lithium cobalt oxide, LiCoO2, has a potential around plus 0.6 to 0.7 volts versus Li/Li. When paired, this gives a practical cell voltage of about 3.6 to 3.7 volts per cell. This is much higher than older systems like lead-acid, around 2 volts per cell, or nickel-cadmium, about 1.2 volts per cell. So, the combination of a very light, highly reactive anode material, lithium, and a strong cathode acceptor like cobalt oxide is exactly what gives lithium-ion batteries their high energy density and makes them the dominant choice for modern portable electronics and electric vehicles. You may need to review the periodic table to look for the materials we talk about here. Electrolyte selection. The electrolyte is the medium that allows ions to flow between electrodes. In a lithium-ion battery, this is commonly a lithium salt, such as LiPF6, LiPF6, dissolved in an organic solvent. The ideal electrolyte is a meticulous substance with a specific job. It must have high ionic conductivity to swiftly transport lithium ions from anode to cathode, while simultaneously having virtually no electrical conductivity to prevent a short circuit. Just as importantly, it must be chemically stable, non-reactive with the electrode materials, and remain safe and effective across a broad temperature range, all while being cost-effective for mass production. Measuring the specific gravity of the electrolyte can be done with a hydrometer or digital density meter. Electrolyte for Li-ion batteries. For lithium-ion batteries, the most common electrolyte is lithium hexafluorophosphate, LiPF6, dissolved in organic carbonates. This mixture conducts lithium ions between electrodes while preventing unwanted reactions with the anode. Li-ion electrolytes are non-aqueous for safety and performance reasons. Recent developments include solid ceramic electrolytes, which are safer because they eliminate flammable liquids. Electrolytes play a key role in transporting the positive lithium ions between the cathode and anode. let's talk about the common secondary battery systems. One of the advantages of lithium-ion batteries is their high cell voltage, around 4.0 volts, the highest among common secondary battery systems. This elevated voltage allows lithium-ion batteries to deliver more power with fewer cells, enabling compact and lightweight battery packs without compromising performance. This characteristic has made lithium-ion technology the dominant choice for a wide range of applications, from consumer electronics like smartphones and laptops to the growing market of electric vehicles. In the comparative table on this slide, you'll see four major types of rechargeable batteries: lead-acid, nickel-cadmium, nickel-metal hydride, and lithium-ion, analyzed across key components such as voltage, anode material, cathode material, and electrolyte. Among them, lithium-ion batteries clearly stand out for their superior voltage, as well as their use of advanced materials like graphite anodes and metal oxide cathodes. Additionally, the trend chart illustrates the evolution of battery performance over time, showing a sharp upward trajectory in both volumetric energy density and specific capacity since the 1980s. This underscores how lithium-ion technology has not only surpassed its predecessors in voltage, but has also continually improved in terms of energy efficiency and storage capability. Please take a moment to review both the comparison table and the performance chart in this slide. They highlight why lithium-ion remains the benchmark in modern battery systems. Lithium-ion battery. Lithium-ion batteries are the most widely used rechargeable energy storage systems in modern technology. They operate by shuttling lithium ions between the anode, negative electrode, and the cathode, positive electrode, during charge and discharge. This simple yet highly efficient mechanism allows them to deliver excellent performance across a wide range of applications, from smartphones, laptops, and tablets to power tools, electric vehicles, and large-scale energy storage. A typical Li-ion battery is composed of one or more cells and includes a protective circuit to ensure safe operation, with the core components being the anode, cathode, and electrolyte. One of the key advantages of Li-ion batteries lies in their high voltage and high energy density. Because lithium has a small atomic weight and radius, these batteries can store a large amount of energy in a compact and lightweight form, enabling longer runtimes for devices and greater driving ranges for EVs. Voltage not only determines the overall energy storage capacity, but also influences efficiency, battery life, and power delivery. Higher voltage systems reduce electrical losses, improve performance, and extend operational lifespan. Taken together, these characteristics make Li-ion batteries the leading choice for powering today's portable electronics and advanced electric mobility solutions. This marks the conclusion of Chapter 1 of the Introduction to Battery Technology course. For deeper insights, please check out the references provided on this page and consult the textbook to further strengthen your understanding of the concepts introduced in this chapter. Once you feel confident with the material, you are encouraged to explore the additional resources available in this module, including recommended YouTube videos and supplementary readings. These will help you reinforce your knowledge before moving on to the practice exercises and, ultimately, the end-of-module assessment. Thank you. We'll meet again in the next lecture.